разговаривать. Так, да. Кирилл сидит, а мы все что-то обсуждаем. Спасибо. Окей. Или это было привязано к ХСЕ? Спасибо большое. Okay, so we are going to restart today our course on dynamical systems. And I recall you that we stick to the part that is associated with Müller dynamics, interval exchange transformations, and billiard flows in rational polygons. So the previous lecture we started to discuss what all these words mean, and we introduced the duality between the world of translation surfaces and directed flows in translation surfaces and interval exchange transformations. So we discussed why the first return map to the transversal for the directional flow in translation surface is exactly interval exchange transformation, and vice versa, how to build up a suspension for interval exchange transformation such that this suspension gives us the surface with the directional flow on it, a vertical flow, and our interval exchange transformation is the first return map to some given transversal. So today we will continue our study, and in general, maybe I should recall that last time we proved the following quite fundamental result. So we introduced who interval exchange transformations are, and we proved the following theorem that was established by Michael Keane in 1975, that almost all interval exchange transformations are minimal. And in reality, we proved more. So maybe you remember that we need two types of information to define our interval exchange transformation. One is a combinatorial part, and this is responsible for the order of intervals on the top and bottom level. So we had actually two lines. One was PT, and the other one was PB, P top, P bottom. And the second half was a metric part. We need to determine the length of interval exchange transformations, the length of the subintervals, in order to fix our interval exchange transformation. So we assume that we deal only with irreducible case, which means that our permutation does not split into two independent parts. It's not the same type of irreducibility that you keep in mind when you teach algebra or study algebra. This almost all also has a rather precise definition. Namely, we require that we don't have any connections. And by connection, we mean that two singularities meet at the same orbit. We also gave a more geometric interpretation of the notion of connection, but it's enough for us to keep in mind this one for a moment. And so once Keane proved this minimality statement, he immediately posed the question. So maybe I don't remember if I mentioned it, but I will say it now, that the absence of connection is a sufficient condition for minimality, but it's not a necessary one. And in particular, there are many examples of interval exchange transformations, the families of them, such that the members of these families do have some rational relations between the length of the subintervals, but however, there are some minimal members of these families. And there is a very natural question. If you have a family that does not satisfy Keane's condition, so the one where you have some rational relationships between the length, if you can suggest some algorithm how to understand when interval exchange transformations are typically minimal inside of this family or typically non-minimal. And in this way, this problem is still open. So there are the only things we know are some very partial results. For example, Mikhail Bashernitsan studied these interval exchange transformations with rational relationships, but only of rank 2. So when all the lengths can be expressed in terms of 2 lengths as an expressions with rational coefficients. So you have only 2 independent lengths. And for that case, he suggested some algorithms that could provide the answer on our question, either the interval exchange transformation is minimal or not. Another example where the full information is obtained is so-called Arnoux-Razi interval exchange transformations. It's a family of non-keen EETs that were discovered by Pierre Arnoux and Gérard Razi in connection with symbolic dynamics. And later, they appear to be very important from many different points of view, including some topological ones. Anyway, this is a family which is non-keen, and where we know the answer how to determine minimal and non-minimal members. But in general, the answer is not known. So already in this paper, Keen posed the question about ergodic properties of interval exchange transformations. And he stated the conjecture that interval exchange transformations are typically uniquely ergodic. So our goal for today will be to make the first steps to prove this statement, to prove his conjecture. But before we will do that, I will introduce a few important geometric structures. So the plan is the following. I start with the definition today. I start with the definition of the Teichmüller space and moduli space. Then I introduce the main tool that we will use to study the ergodic properties of interval exchange transformations and of the flaws on translation surfaces. And I will also think a little bit why the application of this tool can be informative in terms of these structures that we introduce here. And we will make all the preparatory work using this technique in a way that next time, within 1 week, we will be able to prove these unique ergodicity statements. So I will state these theorems today, but I'm going to prove them next time because it requires a lot of efforts from our side. So let me start from the definitions. So I'm given a compact orientable topological surface. And I have a finite non-empty subset of singular points. That's what we had at the previous lecture. And for each singular point, I associate its ramification index. That will be responsible for the angle defect, or the curvature, if you want, around this singular point. And I consider the group of homeomorphisms of the surface such that these points stay at their place. So we fix each point of this set of singular points. then I can distinguish a subgroup of index 2 inside of this group, and the subgroup will correspond to the orientation preserving homeomorphisms. And we can also distinguish the neutral component as the one that contains identity. Now we are able to define the modular group. So be patient, we have a lot of definitions, but we will proceed with some examples later. So we consider those who contain this neutral component, and then we consider the following factor. And we could do the same, adding plus here. I don't want to rewrite, I will just write plus like that. So if you include plus here, you will also have plus here, and if you ignore it, you have no special sign here. So now let us think a little bit what kind of groups did we construct. In particular, how this group acts on the set of translation surface structures. So we have this triple, and we act by diffeomorphisms. So if we had a translation surface, then we had an atlas, because that was the way how we define translation structure, right? So now what happens to the atlas if we take F, which is a diffeomorphism? So we consider the corresponding atlas. And so we made all the preliminary work, and now we can define the Teichmüller space. Here, we just discussed that if we had a map from this group, and we had an atlas that would fix a translation structure, then it was zeta. Maybe it's not beautiful enough, but it was this. So that is an induced atlas that we have. And if the map was nice enough, then you will construct it like that. So what is the Teichmüller space? It's the set of orbits of the action of this neutral component on the set of translation surface structures. On these triples. So what does it mean? It simply means that we assume that, what does it mean, the set of orbits? We say that points are equivalent if they belong to the same orbit. So we consider the action of this group of homeomorphisms that fix our sigma, and we consider those that contain identity, and so we check what happens to the translation surfaces, to the translation surface structures, and if we get two equivalent structures, then we consider it as one point. So what does this mysterious word Teichmüller space mean? Now I need to comment a little bit on the topology of this set. So let me do that. We can consider a universal cover. This is a fixed point member of sigma. And this is a universal cover. So by universal cover, you understand, we mean the cover such that the corresponding fundamental group is trivial. So if we have a translation surface on our tripole, we can define the associated developing map. So we can consider such a map. And we get it by just by integrating from this special point the one form which is given by P star omega, where omega is a holomorphic form that is determined by our translation structure. So if you have a translation surface, you have an atlas. If you have an atlas, you have a one form. That's what we discussed previously at the previous lecture, the duality between these languages. And so you can consider the induced form, and then you can consider such a map. And you simply integrate this form and use this star as a starting point. And conversely, if you have the surface, then you can determine atlas by considering this developing map. And the set of translation surface structure can be considered as a subset of infinite functions on M and C. And so there is a natural open topology. So our Teichmüller space is equipped with a Teichmüller topology that comes from this identification. Now there is a key notion of period map that we will use. Let me give another definition, so what the period map is. So we take a translation surface structure. Then there is a associated holomorphic one form. And we take a relative homology class. In H1, M, sigma, that. So now, you remember that this one form is closed. So since it's closed, we can integrate it. We can consider this map, and it's correctly defined. So if we take F that belongs to diff 0, so F is a homeomorphism, and it belongs to this connected component. So F acts trivially on homologies. But since this action is trivial, then we can consider a map that will take any atlas and associate the map that integrates the corresponding one form over this class in homologies. So it should be constant on orbits of the group we consider. So it allows us to define a map. The map takes elements of the Teichmüller space and take them to co-homologies of our surface. If you want, you can see it as a homeomorphism of H1 M sigma Z C. And this can be identified with the co-homologies. And actually what is true, this is what we call period map. And what is interesting is that locally, period map is a homeomorphism. I will prove it later. Okay, so now we are ready to introduce the next important ingredient of our cocktail. Namely, I gave you the definition of the Teichmüller space, and now I want to act by the group in this space. It's more or less what we discussed in connection with the Teichmüller flow, with the geodesic flow. So my goal will be to define some flow in this space. But before I do that, you remember that the geodesic flow, it was the action of some diagonal matrices, right? Et, 0, 0, E minus T. So we will arrive to something similar, but the first step is to start to act by GL to R in this space. So that's what I want to discuss now. So we are given an atlas that defines the translation surface structure on our triple surface singularities ramification indices. And we have a GL to R matrix. But to think about GL to R matrix, as you know, it's the same as to think about its action on C, on the set of complex numbers. So we consider the atlas that is induced by this action. So it also gives me a translation structure. Translation surface structure, yes? So in reality, what we have an action of GL to R in the world of translation structures. So this action, in particular, commutes with the action of the group we introduced there, with the homeomorphisms. Since we don't touch the singular points, we are in our right to consider it. So we can define a left action on the members of the Teichmüller space. And this action is continuous. So now it's time to use this period map that I defined there. The period map is then covariant with respect to the actions of GL2R on the source and the image. And moreover, we can consider here not the action of the whole group, but the action of some subgroups. And what is the best subgroup? We want to preserve the distances, so we may think about orthogonal part, right? So I would like to think about the action of SO to R. What can I say about this action? We can say that the complex structure is preserved. Good. Now we have a one form, and we have to replace it by another one form. But this another one is multiplied by something that has a modulus 1, because it's all the life inside of SO to R. So the flat metric survives because we can see it as an area. And moreover, this action is transitive if we see it as an action on vector fields. So the vertical and horizontal flow can be replaced by any non-trivial directional flow. So vertical or horizontal flow can be replaced by any directional flow. There is nothing very specific about vertical direction. You can choose whatever direction because we have such a nice description of SO2R action. You understand why we cared about this part? Because at the previous lecture we were always discussing the vertical flow, and now we see that we could easily think about any directional flow. Nothing would change. So I told you that I'm going to prove the proposition about this fact that period map is homeomorphism. But honestly, I think that it's a bit boring, so I'm not going to tell you all the technical details. I will just provide a sketch of the proof and stop there. So what do we need? First ingredient is that period map is continuous. And in order to prove this, you will need to use what I wrote there about the topology, because you cannot define this continuity without such a notion, and you will apply this covariance of the period map that we just mentioned. Then we will use the fact that, as we discussed last time, translation surfaces can be reconstructed from a zipped rectangular model And then in the zipped rectangle construction, what is good is that you can make some very simple manipulation and assume that topology is as nice as we want. In particular, so I will maybe code it by ZR, because otherwise it takes too much time for me to rewrite every time. So when we have this zip rectangle model, what we do is that we assume that A1, which is the first marked point of sigma, is the left endpoint of the whole interval. And then, if we are given two translation surfaces that are close to translation structures, actually at one surface, structures that are close to each other, so they're close to our sigma, and we say that it has the same image under the period map. What does it give us? It gives us the fact that then the subset of C that we have in the zipped rectangle construction is just the same. So they share the space of rectangles for both of them. And then we can build a homeomorphism from one to another one such that their development map would agree. And then we can extend it uniquely to the homeo of the whole M with a star. And this extension is just a lift on M. So these 2 points would coincide in the Teichmüller space. So the idea is very simple. You just start with a period map. You notice that it's continuous. And then you restate the question in terms of zip rectangle model. And for zipped rectangles, it's very easy to see what's going on. And then you go back to the original translation surface because you know that there exists a duality between these two presentations. So now we're going to use this proposition because we want to study some geometric structures on the Teichmüller space. Let's do it. So first, we know that we have a structure of a complex manifold. And we can even compute its dimension. Dimension is equal to G plus S minus 1. G is the genus of the corresponding translation surface, and S is the number of the singularities. It comes from the fact that locally projective restrictions on the period map can be used as charts. So we get the structure of complex manifold. Now I claim that I'm also given a canonical volume form and why we have this? Because we can ask that the lattice given by ohmium from H1, the square has a covolume 1, and then it gives us that normalized Lebesgue measure here can be lifted by a period map, and we have this canonical volume to a Teichmüller space. So maybe you feel a bit lost at this moment. So let's go for the simplest example we can imagine. You remember that we started all this study by the discussion of the torus. It was our canonical object that allowed us to describe the interval exchange transformations and so on. So we do the same. And in case of torus, the genus is 1, and you also have just one mark point. So everything is 1. Then you have one marked point. I define it, denoted by A1, and T is my torus. So I can consider the homologies for T, A1, and Z. And I can fix a basis given by zeta1, zeta2. And in this case, the period map is injective. Be attentive, because if you consider a surface of a higher genus, it's not true anymore. But here it's okay, it's injective. So it's very easy to understand how the Teichmüller space looks like. So you have T, A1, 1, what is it? You fix this basis. And you don't want that the ratio is real. That's how the Teichmüller space look like in this particular case. A square. Yeah, squared, because you need to fix, so you want to fix the basis. So in order to fix the basis, it's two-dimensional, and then they should be independent, these vectors. They should not be collinear. So you should forbid them to be collinear, but then you don't have any other restrictions morally. All the bases, they work fine. So that's what is written there. Okay, so now a little bit more technicality, because in the future, sometimes I will need to work in spaces of a finite volume. So I would like to make normalizations. So we fix the orientation. Let's maybe fix it also. And then we consider only translation surface structures that are just compatible with the chosen orientation. So then we live in the world where everywhere we have to add plus. plus is there in the group of diffeomorphisms, plus is in the corresponding modular group, plus in LGR, and plus is in Q. So it provides us Q plus, GL plus, diff plus. So what can be normalized? The first candidate is area. So you can take an area form induced by our chart. And then we know that it is invariant when we act by the members of this group. So it means that we have a function that acts on this Teichmüller space. So we can consider a locus of the Teichmüller space that would have a volume equal to 1. So this is locus A equal to 1 in Q plus. It just means that we consider only a part such that it corresponds to this. But then this part, apparently, we discussed now that it's a manifold. So when we say locus, we mean that we expect it to have nice geometric structure as well. So you understand, you consider a manifold, and you consider there a part which is identified by some normalization condition. But then, if you are lucky enough and your complex structure agrees with all others, with this area structure in particular, you will have a submanifold. So it's exactly the case here, because this A is a smooth submersion. So we got a codimensional one, a real analytic submanifold. This was when we were thinking about the areas. So now what's going on if we switch to volumes? We consider once again a chart that identifies a set in our Teichmüller space, and then we consider a matrix. And we can, okay, here maybe I should be more accurate, saying that we fix this triple. And then we consider A G star applied to this class. And this can be seen in the following way. So we know also that this Q1 is invariant under the action of diff plus and SL2R. So we can define a canonical volume. Mu will be a canonical volume. And this is just mu1 external product dA on A. And this is what is induced on Q1, a canonical volume form. So this canonical volume form is invariant under the action of people from diff plus and actions of people of SL2R. So in a similar way, as we constructed the Teichmüller space, we can define a moduli space. And the modular space is the result of the factorization of the Teichmüller space. So upstairs, we had a lot of definitions, but in particular, we had the notion of a modular group. Don't be confused with modular surface that we discussed in connection with geodesic flow. Here, it's a slightly different thing. So the modular space is a result of the factorization. of the action of this group on a Teichmüller space. So this is a discrete group, but it acts continuously on the Teichmüller space, and so we consider such a factor. And we could add one here and here, and it would change nothing. Just here, in this case, we would need to add plus. But this is kind of optional. You can erase it, and the statement still will be true. The action of this group is proper, but it's not always a free action. Thus, we cannot say that it's necessarily a manifold. So there we knew that it's a complex manifold, and we even knew the dimension. Here, about the moduli spaces, it's not true anymore. It may happen that it's not a manifold. However, it should be something relatively nice, so it's an orbifold. Not necessarily a manifold. Orbifold just means that it's a local quotient of a manifold by a finite group. So maybe not manifold. That's what we know about modular spaces. And we only need one more important thing, because we want to define the Teichmüller flow also. So I will define marked translation surfaces and marked modular spaces. The reason why I do it, why do we need these marked structures, is because we will work a lot with zipped rectangle models. And there, it's more convenient to deal with marked translation surfaces. So, what does it mean to be marked? If you think about the zipped rectangle model, and you start with interval exchange transformation on the given interval, so we assumed, you remember, that always the left end point of this interval is the first return marked point A1. So at the same time, we know that in our construction, this interval always appear on the surface as an ongoing separatrix of the horizontal vector field. So what I mean is that we mark some particular horizontal vector field once we make this choice that the leftmost end of the interval is exactly the first singular point. Okay? So I will write it up to make it more transparent. So what do? We say that we still fix m, sigma, kappa, but also we fix zeta, the translation structure, because it will be responsible for the outgoing horizontal vector field. Obviously, we require that an isomorphism between marked translation surfaces should respect this marking, the marking of the horizontal separatrices. So we define the Teichmüller space adapted to this requirement. How to do that? You may think about it that it's a K1 fold cover of Q M sigma kappa. Why it's K1? Because there are K1 options which separatrix is the horizontal one. You assume that A1 is the leftmost end of the interval, so there are K1 separatrices in A1, and just one of them is the one for which you will consider the first return map. So these are the number of options. How can we choose this particular direction? Marked translation surfaces are very different from those that we discussed here because they cannot have non-trivial automorphisms. And thus, we can see that this group, the modular group, where it is, just a second, it's there. It acts freely. So there are no orbifolds if we restrict ourselves only to marked structure. We always have manifolds. So we can define a set of marked modular spaces, which is a quotient space with respect to the action of this modular group, and it becomes a complex manifold. And this complex manifold is nothing else but K1 ramified cover of the orbifold that we defined there. So if you want, you can add renormalization. Huh? K1, it's the first element of the set of ramification indices. Because we fixed the set of singularities and also their orders. And so we assume always that the first singularity is exactly the leftmost end of the interval where we define our interval exchange transformation. So there are K1 options, which is this interval where we're going back. So that's our K1. And then if you add here one, add in renormalization condition, you still have a complex manifold, just it will be a submanifold of the original manifold, and it will be a codimensional one real analytic submanifold. So now I'm able to state these theorems about unique ergodicity that I put in a teaser at the very beginning of the lecture today, formally, because we have all the ingredients for that. So let me do so. This is theorem 1. It's by Mazur and Veach, but be attentive, they did not work together. They provided two independent proofs of the same statement. So they say that almost all interval exchange transformations are uniquely ergodic. And the second theorem is that, also by the same group of people, is that the normalized modular spaces M has finite volume. And the action of SL2R on it is ergodic. So these two theorems will be our main goal for the next 1 lecture and a half. And before we make a break, I want to make just 2 short remarks. One, I will give you the definition of the Teichmüller flow, And second, I want to look what's going on in our favorite baby example, when we live on a torus with one marked point. So the Teichmüller flow. We define it on the normalized moduli spaces of marked translation surfaces. And we see it as a restriction of the action of SL2R, but we do not consider all SL2R matrices, but just one parameter subgroup. E t 0, 0, E minus t. So the ergodicity of the action will follow from the ergodicity of this flow. So we are going to prove the ergodicity of this flow. And you see it's very, very similar with the geodesic flow. You probably recognize it. So you can see the Teichmüller flow as a geodesic flow in the modular spaces. Just don't forget which part exactly we call the modular spaces, because we consider the marked one and we add renormalization. Now I told you that we want to take a brief look at the example. When everything is 1. So in this case, our Q1 is nothing else but SL2R, and mod is SL2Z. And so what you have is the normalized modular space is simply the space of normalized lattices SL2R factor SL2Z, which has unit area and on which SL2R acts transitively. So the geodesic flow on the modular space is nothing else than the Teichmüller flow. And you remember that we finished the part about the geodesic flow exactly proving that the first return map for the geodesic flow on the modular space is nothing, modular surface, is nothing else as a continued fraction algorithm. You remember there was this part in symbolic dynamics. So our goal is to check that actually similar statement is true in a much more general framework. And we're going to do it in the following way. we will use our zipped rectangle construction and define some generalization of continued fractions. We will call it a Rosivich algorithm, some multidimensional fraction algorithm, and we will associate this algorithm with the Teichmuller flow. And then we will replace the study of ergodic properties of the Teichmuller flow by the study of ergodic properties of this algorithm. And this algorithm is not something very sophisticated. It's like a projectivization of some linear map. So we will be able to use some standard tools from ergodic theory to get the result. That's the plan. And so today we will complete the first two steps. Namely, I will describe you the algorithm, and we will try to see why it leads us to the multidimensional continued fraction. And next time, we will try to check the ergodicity. So I think we can make a short break now for like 10 minutes. So I will make just one comment. I will explain you how the Rosevich algorithm works in a quite informal way, and it will be different from what will be written in my notes. So if you are looking for some very formal proof, you go for the notes, but if you want to follow just some informal ideas, it's better if you follow what I say now, I think. Okay, the idea is very simple. What is a Rosevich induction? It's a way to define an interval exchange transformation which is equivalent to the original one from the point of view of the orbit behavior, but that would live on a smaller support interval. And the key observation is the following. We start with some interval exchange transformation. You may choose the one you like more. For instance, with this one. And we look for a first point, which is a singular point, but not the end of the support interval, from the left or from the right. I will look from the right. So I will consider this subinterval. It's leftmost and coincides with the end of the previous support interval, and its rightmost end is now the first singular point, which is not the end of the support interval. And I want to consider the first return map to this yellow subinterval. So let's see what happens. First, we look at this rectangular person, red one. The rectangular person goes back immediately. Nothing changes in its life. So all these points, they are back as they are. Good. Now let's make the next step for a triangle guy. Also the triangle guy. Maybe it was smarter. Sorry, I will change the picture a bit. Otherwise, I will have, in reality, less intervals. Okay, so still the triangle person goes back like that. And the rectangular person also goes back immediately. So something interesting happened only to a circular and waved guys, right? So let's see what happens to the circular one. There is one part here. It also goes back immediately, right? This. But then there is one part here that has a different destiny, because it goes here, and it's not included anymore in my yellow subinterval, but these points are all covered by the waved interval. So we associate it with the waved interval, and we go through the waved interval here. So what do we get? We get again an interval exchange transformation. On 4 intervals, the number of intervals did not change, but with different order of intervals and with different length of intervals. So what do we have? This rounded person became smaller. I will mark this waved person. And the rectangular and the triangle, they preserved. So here it's my waved guy. This is my triangle. This is my rectangle. And this is my now small rounded one. That's how the Rose induction works. So let us describe what happened on the combinatorial and on the metric level. So on the combinatorial level, I can give them names, say 1, 2, 3, 4, and they appeared on the bottom floor in the opposite order. So we had 1, 2, 3, 4, and now there's 4, 3, 2, 1. That's what we had at the initial step. What happens here? I can still keep the names 1, but now you see the guy who was 4. Now he lives here. 4, 2, 3. And here they are 4, 3, 2, 1. So from this permutation, we went to the 1, 1, 4, 2, 3, 4, 3, 2, 1. It's a question of agreement how to name them. In some papers, you can see the following approach, that those who live on the top floor, they are always 1, 2, 3, etc. And only the order of the guys on the bottom floor should be changed. But for me, since I care not only about the combinatorial aspect, but also about the metric one, it's more convenient to remember their original names. So now let's see what's going on with their length. Is it clear what happened up to now? Okay, so now let me consider the length. And we had 4 lengths, lambda 1, lambda 2, lambda 3, and lambda 4. And we see that lambda 2 and lambda 3, they did not change. However, something happened to lambda 4 and lambda 1. Lambda 4 did not change its length. It's still the same person. So we can say that it's lambda 4 prime, if prime corresponds to this new picture. But lambda 1, it's the sum of 2 guys. It's the sum of a new lambda 1 plus new lambda 4. So I can say here that it's lambda 1 prime plus lambda 4 prime. So we can say that we had a matrix, a column vector first, and we have a matrix that connects old coordinates with new ones, and you can easily see that this matrix is simply the identity matrix with only one correction, that at the place ig, where this I and G are responsible for the numbers of the intervals who were involved in this business at the very end of the interval, there we get additional 1. In particular, in this case, what we have is that we had 1, 0, 0, 1, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. And this unexpected 1 is this one. And indeed, it lives at the intersection of the first row and the fourth column. And the first row is responsible for the position of this interval, and the fourth is responsible for the position of that interval. So this is an example on which we try to illustrate how our procedure works. Yes, because lambda 1 is this interval. So it's formed by violet part. Yes, it is prime here. Now that's an example. And now you probably have plenty of questions. And the first question is it always true that when we applied the procedure like that to the interval exchange transformation, then we necessarily get the interval exchange transformation with the same number of intervals? Is it true that it's always an interval exchange transformation in general? And then you can ask also more subtle questions. Namely, is it true that if you started with some irreducible permutation and you do these procedures, then you necessarily have irreducible permutations as well, that you could not have reducible ones? So it requires some attention from our side, and we have to think about it a little bit. I proceed with some more formal presentation, but hopefully you already understood the idea. So a few words about terminology. When we look at the, for instance, rightmost end of our interval, as usual, we have two people here, one upstairs, one downstairs. So I claim that if we are in a Keynes situation, and in the case when the permutation is irreducible in our sense, then we can be sure that one interval is always longer than another one. Why it's true? For instance, here I had no doubts that interval number 1 should be longer than interval number 4. Why I was so certain about that? It's rather simple, because there are two options when this requirement could be violated. Either you have the situation when you have interval number 1 both on the bottom and on the top level. But this is impossible because it violates the requirement of irreducibility. Either you had two intervals who had different names but were of the same length. But this would violate the requirement of Keynes condition. We have a rationally commensurable length. So this is not possible, and I can be sure that one interval is always longer than another one. Moreover, I claim that actually even a stronger statement is true. Namely, that apparently if I had a Keen interval exchange transformation, I could apply the Roth induction forever to this interval exchange transformation. This we will prove a little bit more formally in several minutes. So just wait. Maybe I want to make one more comment. So we agreed that they should be of different lengths. And what happens exactly? Let's see more precisely on this picture. The guy who was longer, in our case it's the person number 1, it preserved its position, but it lost its length. So since this guy was able to preserve its position, it's called the winner. And this person, who was the shorter one, this person preserved its length, but it did not preserve its position. You see, it moved here. So this guy is called the loser. So the loser is not the one who is becomes shorter. The loser is the one who has to make the move. The one who will be moved without maybe its own will somewhere at the interval. So when we will use a lot this terminology in the future constructions. And we also need, in order to check that if the original permutation was irreducible, then this procedure did not spoil this irreducible condition, we need to analyze a bit what happened to the corresponding permutation. And apparently, you see what happened, that if the winner lived on the bottom floor, like in my picture, the bottom part was preserved completely. The order did not change at all. While on the top part, the one who was the loser, the winner, sorry, was replaced by a pair. It's a new, his image and the image of the loser. And here we had to forget about the name of the loser. So this letter became longer and was replaced by 2. Then 2 and 3 preserved, but this letter was excluded. So that's what our procedure does. So what would be different if the winner would live on the top floor? Let's make a short picture to understand it better. This will be my winner. Let's say that this guy is here. Then there is a person here and here. So this is the interval on which I'm going to return, right? The left must end as it was, and the right must end as the first singularity, which is a non-trivial one. So as before, I see that this triangle person goes immediately back, and something interesting happens to two others. So let's see what exactly. The first part of this rectangular guy is preserved without any problem. While this thing went here, but this part is not anymore in our interval, so we are going here, and then we are transferred here. So what does it mean? Let's see the coding. So we had 1, 2, 3, 3, 2, 1. And now, what do we have? The upper part did not change. This time the top is preserved because the winner, who is the guy number 3, he lived at the top. He was on the top level. So this time the order at the top floor was not changed. However, as before, the winner is replaced by 2 numbers. Then the rest is preserved, but this we have to forget. So that's how it works. The floor of the winner is completely preserved, while the floor of the loser takes the following change, that you have to find the winner, replace its number by combination of 2, the winner and the loser, and then preserve everybody to the left and to the right of the winner, except the very last element that corresponded to this guy, right? So that's how it works. And in this case, maybe I should mention that this is the winner and this is the loser. So let me draw a rosy diagram. What does it mean? I will explain. Let's take some permutation that corresponded to some interval exchange transformation. Maybe for a moment it will be more convenient to name the intervals not with numbers but with some letters. So for instance, the simplest picture we may think about, the one that corresponded to the rotation on the circle, is this one. So in this we would say AB, BA, and use this as a coding. And then we try to apply the Ross induction. We know nothing about the length. So if we try to apply the Ross induction, we need to consider 2 cases. Because if we have no information on the length, we don't know who is the shortest and who is the longest. So in this case, we can think that, for instance, in my situation, what do we have? B was the longest, so AB had to be preserved. And then we had to replace B by BA and forget this A, so it gets again to BA. So we denote it by the following arrows that started in this permutation and goes back to the same. And then there was another option when A was a longer one and B was a smaller one. And in this case, we had to preserve the down floor, so we would have A, B, B, A. A would be replaced by AB. We forget B here, but we have again the same permutation. So the Rossi diagram is a way to code what kind of permutations we can obtain from a given one while applying the Rossi induction if we have no information about the length. So this is a Rossi diagram in case of two intervals. Now how it will look if we have three intervals. This is the case when we had G equal to 1, S equal to 1, D equal to 2. D is the number of intervals. So here we do have, for instance, ACB, CBA. Let's see what does it mean. I will draw a picture. For example, A, C, B, A, C, B, C, B, A. And if A was longer, then we know that A won, so A should be replaced by ABC, by AB, so we get ABC on the top floor, and the bottom floor would be unchanged. So this is one of the directions. Then there is another option. If B would be longer here, then in this case ACB would be preserved, B would be replaced by BA, and that's exactly what we have here. So you see there are two options, and I will reconstruct the whole Rossi diagram. You can check that it's true indeed. And already here, okay, this one looked like a very reduced case. But this one already looks more general, and you start to suspect that there are some general features that your diagram necessarily shares. In particular, you may see that there are always two arrows that depart from each permutation, but this is what you can imagine just by definition of the Rossi induction, because there are always two options, who is the winner, who is the loser. But then there are always two arrows that arrive to each vertex. And this is a feature that they always share. I will make you one more example of the Rossi diagram when we have 4 intervals. So we start with A, B, C, D, D, C, B, A. That's what I did there, upstairs. And so there are the following options. One is presented there. So what I did here was this IDBC. So IDBC, DCBA. That's what is on my picture. Other opportunities are IBCD, DBAC. IBCD, DACB, IBDC, DACB. And the very last one, what happens there, if the fourth is the longest, then IBCD would be preserved. And then you have DA, BC. That's more or less how they typically look like. So, okay, we understood what the rosy diagram is, and we are missing several important things. One thing is the following thing, that, okay, we know that there is such an algorithm, and we know what is the interpretation if we look at the interval exchange transformation. But we agreed that we always can make a suspension from interval exchange transformation. There could be some small mistakes, but don't worry much. You can check it. So I hope you understood the general algorithm. So now the question is, what to do with the suspension? What happens when we make suspension? Do we understand how does the surface change? And what does it mean from the point of view of the suspension flow? As we discussed, you see I said the Rosy-Veach algorithm, but I always call it Rosy induction, because what we do with intervals and interval exchange transformation, it was described by Gérard Rosy first. But what Veach contributed is exactly the zipped rectangle construction. And so we need to understand what happens in the suspension sense when we apply our procedure. First, let me explain it informally once again in two ways. So let me show you again these pictures that we made here. What's going on when we do this procedure? Now imagine that you deal not only with intervals, but you did the following thing, that I will give you the rectangles whose horizontal side coincide with the horizontal side of each interval. So like that, for 1, for 2, for 3, and for 4. And I will also add the vertical foliation on my bands. Then, if I choose smartly the vertical length, I can use these bands to rebuild my zipped rectangle construction. In which way? Imagine that I take this band and I glue it in a way that it will start here and will go, 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 and will finish here. Did you imagine it? So you give me an interval, and I take a piece of paper and attach it in a way that now its horizontal side will go by this part to where the first interval should be, and by this side where the image of this first interval should be. And I do things like that. And that's what I have, you see, as a suspension of my interval exchange transformation. And I do similar ways these things. And you remember that it is very similar to what we did when we made the zipped rectangle construction. The only difference was how did we make this procedure, that we also added some rectangles, but we had zipped rectangles. So for singularities, we glue these sides up to some moment. And then we varied the rest, right? So we do it here again. And now let us check what happens to these bands when we apply the Rosy induction procedure. Of course, there are intervals. If you have many intervals, there always will be some that are not touched by this procedure, right? For instance, this guy is number 2 and number 3. So if you had some bands attached here, nothing will happen to these bands as well, right? So maybe I should try to make a drawing. What I mean is that I start with some bend here, for instance, and we departed, and then we arrive like that. And we do the similar thing with all the bends we have. Yes, yes, yes. So now those bends that were corresponded to the intervals that were not touched by the Rose induction, nothing happens to these bends. So you don't touch their vertical length as well. And now what happens to this part that was touched by our interval exchange transformation? Look, this purple person goes immediately here, so it's not touched as well. While this guy, this striped one, it had to go first here and then take this rod to go back. So the striped person increased its vertical length because you had to follow first the rectangle number 1 and then the rectangle number 4 in order to arrive to the place where you finally get attached to the support interval. So if you look at the vertical length, H1, H2, H3, H4, that would correspond to the rectangles, you will have the following situation, that I will add primes here, that your H1 prime does not change, it's still H1, H2, H3, they are all preserved, but H4 guy, this person, it now has a much longer trip because you need to add H1 and H4. So you see, while the horizontal length of the intervals, they become shorter, the vertical length of the intervals become longer. And the vertical length of the corresponding bends. And moreover, you can write it formally that if here you had B, here what you will have will be BT. Right? Because if you write it as a matrix, what do you have? You have 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1. H1, H2, H3, H4. And if you look now on this matrix and on that one, you will see that they are just transposed versions of each other. So, but here, don't be confused. This one is an expression of the old coordinates in terms of new ones, and this one is an expression of new coordinates in terms of old ones. So that's what it does with the suspension. Of course, one needs to write it more formally, looking at the formulas we got before, but I hope you believe that it's the case. And the second thing is that what I claim is that the suspension surfaces are always the same, that they are necessarily isomorphic. And in order to see it, you can use a different model, not the zipped rectangles, but the first suspensions that we discussed. You remember we glued it from the polygon, the surface from the polygon with parallel sides. So I can do the same thing. Let me try to make a picture. It's 1, 2, 3, 4. And now I do 4. Then 3. Then 2. Then 1. And now I have to do so this is 1, this is 2, this is 3, this is 4. When I do my Rose induction, what I actually do is that I take this triangle, I cut it, and I glue it here. So the whole procedure simply corresponds to the some cut and glue of the parts of the corresponding surface. You may be more accurate and write what I said here and there in terms of homology basis. But even if you don't do that, I think you already believe in what I said. So the surfaces you get, they will be necessarily isomorphic to each other. And it means that the Rosse induction is a very deep procedure that makes sense not only on the level of interexchange, but also on the level of translation surfaces as well. That you can do the similar procedure with the translation surfaces and then will not change the topology. In particular, that looking at these permutations, you can define the topology of the corresponding map, and the topology will be the same for all members of the of your connected component of Rosse diagram. That's what is important to understand. That if you have a connected component of the Rosse diagram, you may compute the genus of the corresponding surface, and it's the same for all the members of this connected component. Surfaces are always isomorphic to each other when you do the suspensions. So this is an important observation. And now, yes, yes. It may correspond to a different choice of the transversal on which you take the first return map. But you always have the same surface with the same translation structure. They are isomorphic, so it's necessarily always the same. One more thing that could be important. So now the following observation can be done. Is that you remember that when we defined the interexchange transformation, we associated an antisymmetric matrix with each interexchange transformation, looking at who went to the right and who went to the left at the previous time. Now it's a moment when we're gonna apply it. So what we do, first, I want to tell you how to iterate this algorithm. We discussed what happens when we do one step. Now, assume that we get an interexchange transformation with no connections, so we can iterate and iterate. And we can consider an infinite path or a very long finite path on the Rosse diagram. So every time we will get a matrix that would relate old coordinates and the new coordinates. So if you iterate the procedure, it corresponds to the fact that you need to multiply your matrices, right? Because you wrote like old coordinates were b multiplied by new, then new can be expressed as b multiplied by those with 2 prime, and so on and so forth. So the iteration of the algorithm will correspond to the fact that with each gamma, which is a path on the Rosse diagram, you associate b gamma, which is b gamma n, b gamma 1, and b gamma e, SL, that are with the number of intervals. So all of these guys, they have non-negative coefficients. And the coefficients of each matrix tells you how much time we spent, the points of one interval spent on the another interval while iterating. So I claim that b gamma has a quite natural symplectic property, and I proceed with a formal statement. So I fix a finite path. In a Rosse diagram, we started at the vertex pi, and we finish it in p prime. And I associate these antisymmetric matrices that we discussed last time. And we know that the rank of the two are equal to 2G, where G is the genus of the corresponding translation surface. So it's easy to check that apparently B gamma can be used to express one matrix in terms of another one. Because these matrices, they only depend on the order of the intervals. And the B gamma in reality knows who was the winner, who was the loser. So it knows how this order changed, at which places we had to write up once. So this is an easy exercise. And moreover, the following statement is true. So one can choose for each vertex pi of D a basis in the basis. I will consider vectors as rows now, not as columns. In the kernel of this antisymmetric matrix, in the following way, that for any gamma that takes my pi to some pi prime, the matrix of the restriction of B gamma minus 1 restricted to this kernel is identity. In particular, if I have a loop and I restrict just to the kernel, then it will be an identity. So it's very important, the symplectic nature of these matrices. We will use it a lot in the future. And now we are about to check the following thing. You see that I told you that the matrices are necessarily with non-negative coefficients. Of course, there are always zeros and ones. But in order to prove unique ergodicity, I want to apply something like a nested intervals principle. I want to be able to check that if I wait long enough, I will get the matrix with strictly positive coefficients. And how will I use it? I will check that, you see, once for instance, we don't know the length of the original intervals, but we know very well how the Ross induction goes. But then, if you know how the Ross induction goes, you know who was longer than whom at which moment. And then it means that if you consider the simplex of length, every time I tell you that we had to follow this arrow at the Rossi diagram, you can cut a half of your simplex roughly and say that you live on this half and not on that half. And then you iterate and iterate this procedure. And it means informally that you know better and better where exactly did you start. So if you have a very long path, you may suspect that every time you cut and cut some pieces of your simplex, and so you get something like a ray in your parameter space, so you know up to the proportion, you may know where you started. You may reproduce the original interval exchange transformation. If that is true, it's a good reason to suspect that the original map was uniquely ergodic. Because what does it mean to be uniquely ergodic? It means that there is only one ergodic measure. So the natural candidate is the Lebesgue measure, and that means that looking at your map, you can reconstruct the original length, and so it means that your only candidates for the length are those that come from the application of this map, right? From the Ross induction. So if it's true, then you can suspect, if you can reconstruct the interval exchange transformation from a very long path in the Rossi diagram, then you can suspect that it's uniquely ergodic. But why it could not be true? It could not be true, as you know from the calculus course, when the nested sequence does not have one limit. It only happens when it stops to be properly nested, but when it stabilizes at some point. And if it's every time properly nested, then you are lucky and you have one limit. So what we want to do in the next several pieces of our lecture is to check that indeed we have properly nested procedure. And in order to do that, almost always, and in order to do that, we will control these matrices and try to prove that typically they do have strictly positive coefficients. And if it's true, it's not that hard to prove that in Hilbert matrix we have contractive maps, and thus we are in a situation when we have unique ergodicity. And on the opposite, if it's not the case, if you don't have a contractive map, then you may suspect that you don't have one limit, and that's the moment when two measures can enter the field. So this is not the proof at all. It's just to explain you why do we care about all these things that we are going to discuss in the next few minutes. And now we are ready to discuss them. So definition. A finite path in a rosy diagram is complete if any letter in our alphabet is the winner of at least one arrow in the path. So informally, why do we care about complete path? Because you see, from the matrix we wrote there, we have too many zeros. Zeros are our enemies, as we agreed. So we want to kill zeros. That's our goal. But we can kill them only if we have more and more ones appearing at different places. But ones appear only when the corresponding letter becomes a winner. So if we want to be sure that we kill all the zeros, at least we need to be sure that one appears in many places. So that's why we like complete path, and we don't like those who are incomplete. So now we can make a similar definition for infinite path, and there we will increase the level of requirements. So we would like that every letter is the winner of infinite number of errors. So the proposition that will be very important for us is that an infinite path in a rosy diagram is associated to some interval exchange transformation if and only if it is infinitely complete. So what do we mean by this statement? I will try to explain it informally, then it will still require the proof, but maybe you will understand. We look at the diagram. You choose a path for me and ask me, is it true that there exists an interval exchange transformation such that this path exactly corresponds to what happens to this interval exchange transformation? And I tell you that if you gave me an infinite path, it's impossible that the path is not infinitely complete, but there is an interval exchange transformation such that it's his rosy induction way. Why? Because when you look at interval exchange transformation, you see we discussed that we assume that they all have to become winners and losers. All the intervals have to become winners and losers. Why it's not possible that some interval never became winner or loser? Informally, because of irreducibility. Because if some interval always stayed away, too far away from the very rightmost or endmost part, it's strange that it never entered this part. Then you may suspect that the irreducibility was violated. Then if it appears at the very end of the interval, then it should change the roles and be infinitely often a winner and infinitely often a loser. Why it should be like that? Because if it's not the case, what may happen is that if it's never a winner, it means that its length is preserved, right? And what does it mean to be never a winner? If you work with infinite paths, it's the same as to be a winner only finitely often. Because you wait a bit, and then it means that starting from some moment, this guy is never a winner. So his length is always preserved. It never changes. So all other people become smaller and smaller, and this particular nice person does not change its length. This is strange, and in particular, it contradicts the idea that Kuhn reflects in his theorem, that you have everywhere dense orbits. Because Kuhn's theorem, this we will prove formally, but just I want you to follow me. So Kuhn's theorem in particular means that if you apply Rose induction for a very, very long time, you get smaller and smaller interval. It does not stabilize us, right? So then it contradicts the idea that some people may preserve their length, because Rose induction expects that you will become infinitely smaller, and you don't get so. And on the opposite, if you are infinitely completed, then one needs to check that there is a way to associate manually interval exchange transformation to it. So now we will prove this theorem. It will occupy the rest of our class today, and we will prove it conditionally to some result that I delay for the next time. So the proof. What I just wanted to say by all these manipulations is that it's kind of natural to expect that a statement like this one should be true. So the proof comprises 3 steps. First, we need to check that a path associated to some interval exchange transformation is infinitely complete. Second, there will be some auxiliary results. And third will be the opposite direction, that infinite complete path is associated to some ET. So we start with the first part. So let me define A prime to be the set of letters which are the winners of at most finitely many arrows. So we have to prove that if it's associated, it's infinitely complete. Assume that it's not. Because if it's infinitely complete, we are very happy. Assume that it's not. Then there should be a set of letters that win rarely, only finitely often. Or did not win at all. And we associate Tn, it's what we get from our interval exchange transformations, by a Ross induction iteration. And lambda n by n is a column of corresponding EETs. So at each step, as you know, the length of the loser is subtracted from the length of the winner. As lengths are always positive, there should be some n1, which is greater than n0. So n0, it's the moment starting from which people from A prime never win. It exists because the path is infinite, and we assume that it won only finitely many. So then there should be n1 which is not less than n0, such that no letter in A prime is a loser. Why it should be true? Because it cannot be like you have to pay for everything. If you don't want to win, it's okay. But then you cannot be a loser as well, starting from some moment. Because you are big. You don't win, so you don't lose your length. So then you have to be subtracted from others. But you always preserve your length. So how many times you can be subtracted? Some finite number of times, right? So you can be sure that this procedure will stop at some point, and you will stop to be a loser as well. Tn are interval exchange transformations that you get when you apply Ross induction from the original one. So then there should be such an n1 that necessarily you don't lose as well. What does it mean? It means that they do not, these people from A prime, they never enter this rightmost end of our interval. Because they do not win, they do not lose, so they should not be at the end. So it means that for alpha from A prime, necessarily both P top n of alpha and P bottom n of alpha are non-decreasing for n starting from n1, right? So what does it mean? So you look where your interval named alpha lives, and it never enters the rightmost part. But then what happens to your intervals when you apply the Ross induction? Either it was moved, but it does not happen to our person, either it could be pushed because somebody else won. So it could be pushed to the right, but you cannot be pushed several times, because then at some point you will arrive to the very end. So it doesn't happen to us, and we say this. But then, if it's true, then there should be n2, probably greater than n1, such that these quantities are independent of n for n greater than n1. So it stabilizes. Starting from some moment, they stop to change their numbers. It should stabilize. But then if it happens, what is true is that we will get the contradiction with irreducibility, because you may take beta from the complement to this set. And apparently we know that this should be necessarily smaller than what you have for beta. And the same should be true for if you replace top by bottom. And so you know that these guys, they are always to the left with respect to those who are not in A prime. They need to live to the left, while those who are not in A prime, they live to the right. But we forbade it. It really contradicts irreducibility. So this could not happen. Good. And before we will prove this second half, we will state some corollaries from this observation. Corollary 1 tells us that the length of intervals on which that we get as a result of the Ross induction application, they have to go to 0. One ends goes to infinity. Why it should be true? Very simple, because the length of the intervals, they do not increase while we do our procedure. And then we look at the winners and losers. And we may see that, so let's say that each length is a non-decreasing function. And since it's non-decreasing, we can find a subsequence that would have a limit. And so we can define this as a limit. And since it is a limit, we may think that any element here is limited by our limit plus epsilon. And so if we take some other beta, then starting from some moment, we can be sure that beta is the winner of the error such that it's the winner of this error, but not of the next one. And so the difference between the two consecutive steps when both of them do not increase epsilon, so you go to a limit, and then it means that lambda beta of infinity necessarily goes to 0. What we mean is that we always may find a moment such that the winners will alternate. So one guy will not win several consecutive steps. And if it happens, then you can see that their difference should be limited, and since you know that it goes to some limit, this limit should be 0. And another statement that we already mentioned, but we kind of assume that it's obvious, even if it requires a formal proof, is that the Rosen-Witch induction, it stops only if it finds connection. And at this moment, indeed, it stops. So in one direction, it's very simple, that we discussed it so precisely that we both know that if there is no connection, then it does not stop. But what is less trivial is to check that if we have a connection, then we should stop at some moment. And the reason is why it should be true. It's because it will contradict this corollary 1 otherwise. Because if you have a connection, you have a part that will never be reduced. But you should go to as close to 0 as possible. And in order to complete our statement, we will need one more theorem that I will mention, but I will not prove it today. It's quite technical, so I delay it for the next time. But I will use it to complete the proof of this theorem. So this is a proposition by Stefano Marmi, Pierre Moussin, and Jean-Christophe Lecoz. That if we have a finite path in a rosy diagram, such that this path can be written as a concatenation of 2d minus 3. D is the number of letters. Complete path. Then all the coefficients of the corresponding matrix are strictly positive. So if you wait enough, you always get strictly positive coefficients. Almost always, of course. So I'm not going to prove it today, as I said, but I will use it to complete the proof of that statement. So we want to show that if an infinite path can be written as a concatenation of some number of complete paths, then it is associated with some interval exchange transformation with no connection, and it is associated through Rosen-Witch algorithm. So the idea is the following, that you consider the convex open cone. And we consider the part of it that corresponds to our path So set of length data that correspond to gamma. And by this proposition that I left for the next time, we know that the closure of this guy is inside of Cn with 0. So it gives me the fact that 0 with C of gamma is intersection of Cn. So I need to check simply that this person is non-empty. And that's where I will use this argument, which is basically based on this nested sequences idea. Nested intervals, nested simplices. So I construct Cn and this, and then I consider the intersection, and I check that the map is always contractive in projective matrix, and so I will get the limit, and this limit will be my interval exchange transformation. I want to stop here, and next time we will use all these constructions to prove the unique ergodicity statement that I announced. Thank you very much for your attention.